Um, so almost everything I will say in this lecture is joint work. I should say in progress, like I'm holding back the writing. Um, it would have been done a long time ago, or not me, with Yoel, Groman, and Umut. Um, so I'm going to just start with some statements. What will be so this will be a paper on as soon as we finish, right? Um, so statements of the main result. Let I'm not going to say this here. So let M be a closed symplectic manifold. So implicitly there is a symplectic form. Closed manifold. Uh, associated, and this is now the beginning of the statement, to each compact subset. K and M is a category okay, let's call the category F sub K of M. And the way that we read this is that is the Fukaya category of M with support on K. Whose objects are Lagrangians in M. Okay, so the objects somehow don't depend on the set K too much. Or the way we're writing it, actually, they really don't depend on the set. Okay, with extra data. This is the extra data that I'm refusing to explain what it is, and I will continue to refuse to explain what it is. And equipped. And this is a category which is like, so we have fixed some, we fix K to some kind of ground ring. And just so that it's, don't for, you know, there's already so many technicalities, let's set it to be of characteristic 0. Not going to be clear at all from my lecture why I'm fixing this. And in fact, now with very modern technology, it should be possible to eliminate this condition. In general, but for now, I don't want. Let's not do that. Let's just, use more standard techniques. Okay, so this so we're going to fix this, and then this is like before going to be some category that somehow lives over some disk. Okay, and we're still not I still have not said anything too precise about that. And that will be in about 15 minutes, maybe 20 minutes.
How does it react to K?
Oh, absolutely, completely different things. That was horrible. I know. K is a compact set and K is a ground ring, and they're unrelated.
Sure, but the K on the right-hand side, how does it enter the definition of the K?
I haven't. It will. I'm going to formulate some additional structures that will make clear how. I mean, later I will say exactly more about how it enters, but right now I will say some words that will explain what that means. Okay, so there's something associated with thing. How does it enter? Well, one way that it enters is as a functorial with respect to inclusions. Okay, so associated to each inclusion. K inside K prime is a functor f K prime. Um, um, K enter. So in words, if you have something and it is supported on K, okay, and K is a subset of K prime that in particular is supported on K prime. Now, this functor is going to be the identity on object. because my objects are always the same. They're just Lagrangians in M with extra data. So it enters only in the morphisms. So somehow, whatever the morphisms are in here, and let's actually just introduce that notation now. We will write C F star K L L prime, let's say L0, L1, for the morphisms. It's unusual notation, but somehow it's some kind of standard thing in the subject. This says this F here is for Fleur and this C is for chains. It means Fleur chains, branch. Okay, so there's some categories, K-linear, it has morphisms. These are the morphisms that lives in this guy. I didn't write that over here. That's impossible. So there's some kind of restriction. This restriction functor is strictly functorial. So,
You call it restriction, but you go from K to K prime.
Yeah, that is full restrictions.
Sorry, give me 1 second. Yes, I should call it that. It's actually, sorry, it goes from K prime to K, and this is not how I should have said it. I really should have said it as restriction. So what I said was, as a motivation, I said, oh, we have supported on K.
I mean, it doesn't make sense.
Just give me 1 second. So this is what I want. So this is the correct statement. This is the correct statement. You go from the big thing to the small thing. You take sheaves on some big thing and you restrict them to a small thing. Okay. Right. Okay, so we have this inclusion, the restriction map. This restriction map is strictly functorial.
No, if you have an object that supports 2K.
I know. So maybe the terminology. So maybe the terminology supported on K is not exactly the right term for what it is here. I don't have. You see, right now I haven't said enough to explain what I'm saying. But if I did it the other way, there'll be some nonsense and I would have a ring, I would have zero mapping to a ring with the units, and that wouldn't make any sense. So this is the only thing that we know how to do it makes sense. Okay, so the restrictions, Oriel?
If the objects are Lagrangians in M,
Yes,
that was a statement for any K.
for any K.
It's the same set of objects.
Yes, yes. Right. Those objects, for any K. And most importantly is that right now our version is this extra data kind of doesn't depend on K. So the initial thing in here, so there's all these categories. The biggest one is actually the Fukaya category of M itself, with support on M, which we just called Fukaya category. Okay, strictly functorial. So what that means is that, now we take K inside K prime, inside K double prime, and then you just have okay. And great. And then there is now some two additional properties, okay, such that which are part of what has to be proved in order for this to be a meaningful notion, such that the following two properties. I mean, there's more things, but these are somehow the key things. So the first one is something that I like to call the Rule-Lagrange descent. So this was first appeared in Umut's thesis. And I'll first state it, say some version of it. So if the characteristic, so if K1 and K2 are compact subsets, subsets whose indicator functions Poisson commute. Indicator functions will commute. Then, well, then you have something like a sheaf property. So I'll write it just at the level of morphisms. You have this big set, which is their union. You have this small set, which is the intersection. And you can restrict in two ways. And the statement is that, well, if you were to take this thing, this diagram commutes, and this total thing is acyclic. But another way to put it, roughly speaking, is that this chain complex is obtained by moving these two chain complexes here along the restriction map. So the total complex here is acyclic. And then 2, which is in some sense the fundamental property that makes it makes symplectic topologies of studying symplectic manifolds somehow more rigid than studying other things. So if I'm going to ask the question, when yesterday was a question like, can you do this for BV things? Or I said, well, usually I'm asking you to do this for Poisson things. Like this is the thing that I don't know how to, even I don't know how to imagine proving something like this. So it's called from vanishing or displaceable sets. So if K admits a displacing Hamiltonian isotopy, I'll explain what that means right now. I.e., if there exists, let me just say, HT 01. So this is a family of maps from M to R, such that if I flow along the Hamiltonian vector field of HT, so this is the vector field that's defined by the property that omega of HXT with any vector V is VHT on V. So if there exists a Hamiltonian such that the flow along HT has the property that takes K to a subset, let's call it phi of K, let's call this flow phi, such that K intersect phi of K with the empty set. Okay. Then what you conclude is that what we prove is that this category or here are the morphisms, but okay. Let's just say category F K has the property that all objects are acyclic homomorphisms. Acyclic away over the punctured disk. So I gave some analogy. Again, these categories should be thought of as moving over some disk. I still haven't precisely said what that means, and I will do it later in this lecture. But that means in particular, you can take it over the function. And this should be, so this is some phenomenon of what we call symplectic rigidity, which means there are some sets for which this is not possible. Okay, so let me now give an example of what, what this kind of just these two properties tell you. It won't give us a computation, but it will tell us something interesting. Yes, question.
Clarify one indicator function.
Yes, great. So let me just do something. So the easiest, instead of giving a complicated explanation of what I mean, I want to say how this comes about in practice. Okay? So in practice, one arises from integrable systems. So let's just assume that we have some map from M to some base B, okay, such that whose defining functions Poisson commute. Let's call this pi for now. Whose defining functions Poisson commute. So the simplest case, of course, is going to be where B is one-dimensional. If this is just B is like the circle or R, then there's just one function, okay, that's defining this map. B is a manifold. And then in that case, whenever you take any two subsets of B and you take their inverse images, you're going to have this property. And setting AI to be pi inverse of some subsets inside B, they need some names. Let's call them BI. BI subset of B, get property one. And this is how it's used in practice. And that's now the example that I want to explain. And the idea basically is like, well, whatever the characteristic function, it's not a smooth function. So what do I mean by Poisson commutes? But in this case, I think this is just a much better way to just say it. In practice, that's what it means. Okay, so let me just do an example for what this means and how it's very, it's kind of likely strange. So let's take M who's S2. And the first thing that I want to point out, so on S2, there's this equator. And now what I want to say is that, well, if you take something which is not quite the upper hemisphere, but something slightly smaller, then this case satisfies this property here. So any disk which bounds, which has area which is less than or equal to half the total area, so it's strictly less than total area, is displaceable. What's the displacing isotopy? Well, it's kind of actually hard to write down Hamiltonian to do it, though you can do it. What you do is you just take this picture and you just rotate it to the other side. Then you see a disk at the bottom half that doesn't exist, that doesn't intersect the top disk. So this is now 0. And so using, on the other hand, this S2 has an obvious map to R, which is a moment map of the circle action, but for me, just okay. And using the second property, that now tells me, for example, that if I wanted to compute for the whole thing, the invariant, so this is K. Now let's make this K1. Did I call them K1? This K1. And let me have color somewhere. I have color somewhere. Now let's make this K2. So I go to this formula and it tells me, okay, so if I want to compute the thing for the whole thing, CF star K1 union K2, well, that in this case, that's all of M. Well, what I need to do is I need to compute for K1. Sorry, this was called L0, L1, just so that I wouldn't get confused. And I need to compute for the other one. And I need to compute for the intersection. Okay. But now, if I'm working away from the, working over the punctured disk, then I just said that this one is 0 because K1 was displaceable. Okay. Again, not if you work over the full disk, it's not true. There's some stuff at the origin that you would be always neglecting. That one is 0. And this one is a fortiori also 0 because if there's some kind of, this is a map, there's a functor. So if something is already 0 here, then it's going to be 0 there. Alternatively, K1 is displaceable, so the intersection of K1 and K2 is also displaceable just by the same thing. So this one is 0. That means that these two things are equivalent. And so, okay, so that's interesting. So now everything lives only on the K2 part. But now you can do the same thing again for K2 and try to break down K2 into some the only difference between K1 and K2 is that K1 is a disk of area less than half and K2 is a disk of area bigger than a half. But inside this disk of area bigger than a half, do the same for K2, and let's just make that to be kind of a union of a small strip around the circle. To call that, I'll just call that. I'm just going to decompose it like this: K3 union K4, and let's just draw them. Okay. This is going to be K3. And the last one is going to be K4. And so again, the same thing will tell you that the contribution of K4 is 0, and you conclude from this that CF star L1, L2 mapping to CF star of K3 of L1, L2, that this is some kind of equivalence over the punctured disk. Okay. So this says somehow we have this thing over the punctured disk, everything is supported in a small neighborhood of the equator. Well, let me just say all the morphisms, all morphisms, let's say. Okay, I still haven't told you anything about how this is done, but I've just said, formal applications of the properties that I mentioned. So now I wanted to say that somehow this is very puzzling from a certain point of view. because we saw already K3, well, K3 is a very nice symplectic. In this case, the theory is done so that we can have any compact sets. That's very general. But in this case, my examples are like, everything that I'm doing is with compact manifolds with boundary. So warning. And that's what this warning was for. Even when K inside of M is the inclusion of a codimension 0, symplectic submanifold, with boundary, then there are two things that you could study. You could study this thing that I'm introducing, this kind of F of K of M, but you could also study F of K itself. And okay, so this has things which are Lagrangians in M, and this has things which are Lagrangians in K. Okay, would make sense. And there is some kind of thing you could do on objects, which roughly speaking would take L to L intersect K. But what this will tell us, and I will say a few words about why in a minute, what this will tell us is that there is in general, even if such a map were to exist, it's certainly not an equivalence. So. And moreover, in general, it cannot actually. But in general, there is no such function. So why is that? And this, again, we can. So the only thing that I would need to show that is one computation, which of course I'm refusing to do because I haven't told you the guts of the proof. So to see that, we would need to identify some object in Fukaya category of S2 would support on the whole space, okay? With non-zero, and compute a Tom. And this object, you can imagine, again, so there's some Lagrangians, and I said Lagrangians are curved, and it's already looking like there's some very special curve floating here. This object would be the equator. IL. And then one can compute, maybe again 15 minutes, we'll start to see why. One can compute that CF star over S2 of LL is just, as a chain complex, has cohomology isomorphic to the ordinary cohomology of the circle. Okay. So that looks pretty good. I mean, that's somehow, I'm just asking you to believe me if that's the case. Shouldn't be too unreasonable that this is the right answer. I will warn you that it's not true multiplicatively, it's only true additively. But now we can use that for something, okay? So we can use that I mean, there's multiple ways we can use it, but the simplest way we can use it is I will remind you, call.
You mean by that that it's only at level of vector spaces and not of algebras?
Absolutely. Absolutely. The multiplication is not the usual multiplication, it is somehow deformed. Okay. So, one of the other things that I, so now, so this is the case, and then by this, by all these statements, what we know, and let me just go to K2. So the above discussion. It implies that CF star, just right here, K of L equator, let's call it L equator here, so we have some equator, L equator, is also isomorphic, to the cohomology of S1 if if K is a disk of containing the equator of area bigger than half. I'm just saying this containing equator. That's okay, we take a disk. That's the case. Okay, so now I was saying I'm saying this because I'm trying to explain that there in general we cannot expect such a thing. So let me continue a little bit more. But now let's do another symplectic manifold where the same case sits. So instead of taking this sphere, let's instead just look at a plane. And equals C. And then I just take this disk K and I just put it in here, same disk. And then there's this equator. Now comes the punchline. The punchline is there's this vanishing for displaceable sets. Okay? And the vanishing for displaceable sets tells you that now so this now the notation unfortunately is not great because this is for CF star for K as a subset of S2. And this tells you that CF star K is a subset of C. This must be acyclic. Okay, because again, in C, there is just the Hamiltonian isotopy is you just translate using the function, which is like y, and that will just move things in this direction. This will be disjoint from itself. And then this tells you that this must be 0. So they're not, if there was a principle that said that, these things are equivalent to each other, that you can just look at the thing and put on the set, then, we'd have to break down in one of these. You'd have an equivalence between these two things, and that's not possible. Yes.
Sorry, silly question perhaps. You split the sphere into 2 parts and then reduce it to the equator. Why can't I split the band around the equator into 2 parts and restrict it to the overlaps of these parts?
Great.
And then you have open sets and that's 0 again.
That's exactly correct. That's exactly great. Great observation. Because that would violate this Poisson commuting property. So in dimension 1, it's very easy. This Poisson commuting property essentially comes down to, do the boundaries intersect? I mean, for domains. And I was very careful to make sure that my boundaries never overlapped. And for that, then it's very easy to make them. But as soon as the boundaries will intersect, then one of them will define by partial x, and the other will be defined by y. Well, these things don't Poisson commute. Absolutely. Yeah, great. Okay. So that's the warning. These categories with categories of support. Again, I understand there's terminology may not be so great. They exist. They have satisfied all these great matrices, but they are definitely not. The morphisms really depend on the inclusion. Okay, and then the thing to say, however, which we are not going to get, we're not going to get to, is that there are very special situations where we expect that there is such an equivalence. Okay, and when that holds, we say that locality holds. Okay? There's special cases where we expect equivalence in here. Okay, between this category and this category, probably only up to subtriangulated closure. Let's not worry about that. Okay, and when that holds, we say, as I said, there's some term that we use that's called locality.
But there's always a functor in the other direction.
No,
Uh,
no. So naively there is a function in the other direction. So take a Lagrangian containing K and just consider it as a Lagrangian here. But that would have to respect morphisms.
yeah.
And let's point out that basically here, what's really going on is that if I just tried not to, it turns out that if you try to compute for the disk itself, with K is this disk with boundary, then you already get 0. So the problem here is actually not on this side. On this side, everything is okay and it's 0. It's on this side that things are not okay. Okay, and that's the this Lagrangian this equator, if considered just in the disk, actually has 0 morphisms. But if considered as something living in the Fukaya category of S2 with support on the disk, then actually has non-zero morphisms. That's the part that doesn't make sense. Okay, so now I will try to say some words about why all of this is happening. But now I have to start saying some words about Floer theory. Like I've talked for more than 2 hours about Fukaya categories, and I have not said the word to the holomorphic disk, and now it's time to do it. Okay, but any questions first? Okay, so the first thing that I need to do is kind of just stop saying these words about supported on the disk, on the punctured disk and the disk, and I just be more precise about that. And I just will ask you to accept that these words about disk and punctured disk accurately reflect what I'm about to say. Box. So, if you are doing algebraic geometry and you say something lives over the punctured disk, well, or the disk or the punctured disk, that means something like you have some kind of power series ring, or maybe like a ring of like polynomial ring in one variable. Okay, and that variable is recording which point on the disk you're on. So in Floer theory, unfortunately, we do have something like that. So we're going to introduce a formal variable. T. Okay. This is for the base of this for the coordinates on the punctured. This is the coordinates on the punctured disk. Coordinates on the disk. And the nicest thing to do would be to just take something like that, power series in T, and this is functions on the disk, and then K, T, T inverse. I mean, of course, the nice thing to do actually is to take like polynomials in T. Somehow, you'll see in a second why that doesn't work. Okay, but this is not what we do. We do something very similar to this. This includes, inside what we call the Novikov ring, there's a K somewhere hidden. Let's not write it. So this is the Novikov ring. And it consists of series from AI e to the lambda I, okay, where AI is in K, and lambda I are real numbers, but in this case they're positive. And then, just like in power series, you take an infinite sum. Well, the only way for it to make sense is if the exponents go to infinity. Similarly here, the exponents go to infinity. Okay. So that's some. So when I said something lives over the disk, it means that it's linear over this category. That's what it means. over list formally means linear over and this. Okay, that's the definition. And living over the punctured disk means linear over the same thing, but now inverting, joining 1 over t. But it turns out actually in joining 1 over t, this is the same ring as something we call just the Novikov field. We call this the Novikov field, even when k is not whatever terminology. Field. And it's the same kind of thing here. Elements are some ai t to the lambda I. And now again, ai like these are kind of coefficients in k. And lambda I is just real numbers. But you see, just like in here, when you know, there's some kind of asymmetry between t and t inverse. So in t, you have power series, in t inverse, you have only finitely many terms. So similarly here, we still have the limit as I goes to infinity of lambda I equals plus infinity. Okay. So this goes from I equals 0 to infinity. So series are only one direction, but some negative terms. Okay, so why does this, you know, what is the role of these things? So that's going to take a couple of blackboards, but before getting there, I will simply say the following thing. We are going to still remember Lagrangians are basically our objects with extra data, which we're going to ignore. Okay. Lagrangians are our objects. So we're going to define morphisms. And morphisms, when we define morphisms as modules over these rings, it's not at all clear that we need to use these kind of variables. We can just define some kind of modules over k. In fact, just define the pre-abelian groups. Nothing is going to be, will be no obvious appearance of either the ring k or this formal variable t. But that's just as modules. And then we have to define a differential, or we have to define composition. And when we do that, then we will have to introduce these variables. And if we try to avoid introducing these variables, for example, by setting t equals 1, which is the tempting thing to do, because that's this exact case I talked about yesterday, then we will have non-convergence of our expressions, and it won't make any sense. So these t's are here because we want to count something, and there'll be infinitely many terms, and the only way to do algebra with infinitely many terms is to, well, a standard way to do algebra with infinitely many terms is just introduce a variable that keeps track of these terms. Okay, that's the preview for the next 5 minutes. So now, okay, so given L0 and L1 inside of M, we define this thing, the F star, and so far there is no K. This is the global thing. I will get to the support part later. So F star L0, L1. Well, we can't really define it in general. We can only define it under some generic assumption. So given L0 and L1, which are transverse? First, so we define this to be the free, okay, module. Let me just write module generated by the intersection points. L0 intersect L1. Now you can object, like this makes no sense. This way, I haven't even defined this CF stars. This is like the morphisms. And this is the module underlying morphisms in this Fukaya category M L0 L1. Okay. The way I defined it, it makes no sense. I haven't even said what it is for L itself because L is not transverse to itself. So I'll just remind you that the Lagrangians are half-dimensional. So generically, we'll call dimension of L equals 1/2 of the dimension of M. So transversality says that generically L0 intersect L1 consists of, well, it really consists of finitely many points if the LIs are compact. Okay, so if this bothers you a little bit and you would like to make sure that we can do CF star LL, we can generalize this to some case that L0 intersect L1 consists of submanifolds that meet nicely enough. Okay, is nice enough. Don't want to get into the technical term, but it certainly includes the case where they're equal. In which case, okay, instead of getting points, we should just get the cohomology of the intersection. Maybe some kind of chains on it. Okay, so it's still a bunch of nonsense. Now I should draw some pictures. And I'm going to draw my pictures on Riemann surfaces. Pictures. Okay. So again, I could really do any Riemann surface, but it's convenient to do S2 because that's what we've been talking. So I draw S2 again. And instead of doing, so I'm going to take this, my equator L. And then I'm going to take this to L0. And then I'm going to take another equator. One. That's what I want to do. And I see it's obvious. I mean, the intersections consist of 2 points. So in this case, what am I trying to say? Well, in this case, this has rank 2. It's pretty good for being the cohomology of the circle, which is what I promised. Okay, so now, I've been saying these are linear categories, so I'd need to define some differential. I've been saying there's chain complexes. I need to define some differential. And so to define differential, we need to choose some extra structure. So let us pick. So now we need a little bit of linear algebra, but let me say it like this. We may pick what is called a compatible, well, what did I say? An almost complex structure on M. Okay, let's call this J. So what does that mean? This means like some endomorphism of the tangent space with J squared equals minus the identity. Okay. Well, on S2, this is pretty obvious. I just picked the standard. This is a Riemann surface. So we just do that. On S2, you can just use usual complex structure. So in general, it's it's a little bit of linear algebra. So M is symplectic. So M is controlled. So in general, what's happening is basically the structure group of this vector bundle Tm is the linear symplectic group SP2NR. Okay, this is the linear symplectic group. And this linear symplectic group has a maximal compact, and this maximal compact is actually UN. And the fact that the maximal compact is the unitary group tells you that you can reduce this, and the fact that the inclusion of the maximal compact is homotopy equivalence tells you that you can reduce the structure group from the symplectic group to the smaller thing, and in the smaller thing, of course, you have a complex structure. That's how it exists. And now, using this, we can finally write something, which is going to be the differential, and which is going to justify, I should have erased the above thing, which is going to justify why we introduce these rings. So, so given a pair of intersection, so intersection points, we can, so let's get x and y, define vxy, and this is the structure coefficient of the differential matrix. To be the count, whatever that means, of solutions to some equation. Equation to some PDEs. So this PDE is like a map from strip. This is R times 0, 1, mapping to M. Boundary maps to L0. This boundary map to L1. And at infinity, it maps to X, and infinity maps to Y. You want to count all such things. Okay, we'll not get into details, but what I will say is that if you look in this case here, what you see is on strip here. I didn't write it. Satisfying some equation, but I didn't write the PDE, such that, let's call this map U. So the Riemann surface, this is some Riemann surface sigma. Okay, it has coordinates S and T. This is S and this is T. So it has a complex structure, J partial E equals partial S. So you got it right. Such that du composed with J equals J composed with du. Okay, so this is what's called the holomorphic. This is sometimes written as del bar U equals 0. Okay, so if you look here, you know, and on Riemann surfaces, we have Riemann uniformization. So it's really, really easy to find such solutions. You just draw some pictures like that. There's one here. There's one in the back. But actually, there are many, many more. So by that, I mean, if you think about it carefully, what you can do is you can write some map. So you can take these things and you can add to it some extra, something that covers either the upper half plane or the lower half plane. There are, in addition to the obvious strip. We can compose with some kind of multiple covering map and compose with multiple cover map. And get things that wind around multiple times. Okay? Like you can get things that have like multiplicity, K here and, you know, K prime here. I mean, the K's are bad numbers. I don't quite know exactly how to say this, but because they're a little bit hard to draw in this case. Okay, so what's the problem? The problem is I said we should count something. And at the same time, I said, well, there isn't just this one and this one. That would be great if there were only two of them. There are other things that wrap around multiple times. But when they wrap around multiple times, they have to pick up some area. And that is exactly why we introduce these rings. So in general, the count has to be weighted by area. And the area is very simple. You have this U, this map U from M, and you just take U upper star of omega. That's a 2 form on the Riemann domain. Form on sigma, and then you just integrate this. Okay. And if you just took an arbitrary map from a strip to this target, this would be a real number. But this is actually, this is positive. So this is R. This is a real number, but in fact, this is strictly positive. Right. Strictly positive. If U solves this equation, if d bar U is. So what does it mean to weigh something by area? It means that, say you're gonna count them, there's like finitely many of them. You're going to get some expression, which is sum, maybe plus or minus 1. We can just worry about that later. T to the integral of u upper star, ui upper star of omega. Okay. So you just put it up in the air. This is the area of each contribution. We're still not done. We're still not done because somehow, just because I said we should weight it by the area doesn't mean that this sum is finite. Because it could be that there's infinitely many things of area like 2000. And then this doesn't make any sense. But there is fundamental result in the subject due to Gromov that says that in fact, this sum, while it's not a finite sum, is convergent Gromov compactness. Converges theoretically, but that means basically, i.e., this matrix coefficient dxy is well defined as an element of this ring. You take the sum. If I say I only want to look at things so that this exponent is less than some given number, like 1 million, then there will only be finitely many terms.
But that area you drew there, will it count as 0?
No. In this world, this will not count as 0. This will count as whatever this epsilon is.
Twice.
Yes. So over a field of characteristic 2, it'll count as 0 because there'll be something, t to the epsilon and t to the epsilon again, and you add them, you get 0. And if you do signs very carefully, you will get +1 and -1. Okay? But now I do want to say something, which is what happens just to illustrate how delicate the situation is. Okay, for people who haven't seen this before. But this was for the 2 equators, and for the 2 equators, the key property that happens when you have 2 equators is that these 2 areas are the same. But what if we don't pick 2 equators? What if we shrink one of the 2? One of the 2. So how do we do that? Well, there's many ways to do this, but we can just move it up a little bit. Okay, I took one here and I just moved it up. Now suddenly, this one is big. Like this is like t to the epsilon, and this is t to the epsilon squared. Well, it's small. And now it doesn't matter anymore what the signs are. This tells me that dxy is t to the epsilon squared plus t to the epsilon, maybe plus or minus. Maybe there's some higher order terms. What I'm telling you is not exactly the truth because I'm omitting some extra structure, but this is the key point. Well, this differential is non-zero. Okay, so this is non-zero differential. And what you conclude is that the homology is trivial over this ring lambda. So why is it trivial over lambda and not over lambda naught? So let's simplify everything. Let's just, this is higher order, so it's all about this. Okay. If I tell you that I take some map and t to the epsilon square, I don't know why I did that, but anyway. So we have a free module, lambda naught, and then this is multiplication by t to the epsilon squared. Okay. Well, this map is injective. Okay. When you compute homology, you look at the kernel modulo the co-kernel, but in this case, on this side you look at the kernel. Well, there's no kernel. Okay. And on this side you look at the co-kernel. Well, the co-kernel is lambda naught modulo t to the epsilon squared lambda naught. Okay. Well, this is a torsion module. It's a torsion T module. If you invert T, then this becomes an isomorphism. So if you invert t, this becomes an isomorphism because the inverse is like t to the minus epsilon squared, and then, well, if you take a chain complex with two parts and the map between them is an isomorphism, then everything dies. So that's how subtle. That's the subtlety. That's what we mean. Okay. Well, unfortunately, I have to keep going. But if there are any questions, this is a good place for it because we're about to get into even more stuff. Okay. So far, I've just talked about Lagrangians and how to do some kind of to define. This is called the flow groups. What I really need to do next is to what I need to do next is to tell you how the morphisms in K depends. The morphisms in this category with support on K depend on K. That's a real goal. How does K enter the picture? That's really what's going on. What we need to do. Well, it enters via its characteristic function, but we need to get there, or some version of its characteristic function. We need to get there. So first, the preliminary. Let's say that we have some Hamiltonian. So some this we're called think of a time-dependent Hamiltonian. Let me do the simplest thing here. So this is like before I wrote like h sub t from n to r for each t in the interval 0. So given such a Hamiltonian, what I can do is I can define a kind of variant of these flow groups, a variant that incorporates the Hamiltonian. And define df star. And now I'm going to put an h here. Okay, and this h down here is intentionally there because later we're going to define the thing for k in terms of these things. So notation may be a little bit confusing, but in principle, there should be this J, this complex structure that's used to count pseudo-holomorphic disks. But we're not going to. I'm just not going to write it. Okay. To be F star L0, and then here I'm going to write phi h of L1. So there's always these conventions about whether this phi h should go here or here. I'm not giving anything at the correct level of precision for it to matter. You can just trade things around. So let's just put it there. It's convenient to put it there. Okay. So what do I mean by that? Well, I've told you that if you take some Hamiltonian that has a flow, phi h, which is generated by the Hamiltonian vector field. Okay. And so therefore you can act on Lagrangians. So it seems like we have done almost nothing. I've just said that in this kind of setting associated to two Lagrangians, there's not just one group, but a group group for every choice of function h. Okay. So now remember in the end, or at the beginning rather, I started by saying we're going to define these things and they're going to be functorial. Okay, there's going to be something associated to every inclusion. And that statement associated to every inclusion, it comes from some statements for every function. So this is the key thing that's going to give rise to functoriality. So we want to relate CF star L0 TH L1 to EF star L0 P, let's say H prime L1 for different Hamiltonians. So if you have heard about Floer homology at some point, before this talk, you were subjected to a talk on Floer homology, then you probably heard something about Floer homology is Hamiltonian invariant. Okay? And Floer homology Hamiltonian invariant essentially means this group is equivalent to this group is equivalent to, where did that one go? The one with the H only. It's gone. Is equivalent to this group here. They're all isomorphic, but again, they're chain complexes. So when you pass to homologies, the homologies are isomorphic. And that statement is true. People didn't lie to you. But that statement is true over the punctured disk. Okay. And over, the non-punctured disk, that is not correct. Okay. So, what is the, so what, no, now I need to explain what happens in general. So the correct statement it's a kind of well-known principle in symplectic topology, but so if with another variable h and h, let me just do what do I call my sets? I call them h1, h1 and h2 functions of m with h1 less than or equal to h2 everywhere pointwise, then we have a map T F star H1 of L0 L1 F star H2 L0 L1. And this map is essentially canonically defined, but the most important thing, it is a map of modules over de Novi covering. Map of modules over. How is this map defined? So to define it, you do the same thing as what we did with define the differential. To define it, you just interpolate between H1 and H2. And then you draw this picture. So at the top, that's not what I normally do. At the top, you put L0. And now remember, I basically defined this group to be the group where I just apply the Hamiltonian diffeomorphism to L1. So over here, I better have B1 of L1. And I better here have B2 of L1. And in between, I had like phi, let's say sub S of L1 for this fable. And then I write the same equation. This is U, which is a map from R times 0, 1, M, and then I require D bar U equals to. You can just write this. And that what that will do is that there is some intersection point x1 and some intersection point y2, and so x1 is an intersection point of L0 with P1 of L1, and x2 and y2 is an intersection point of L0 with phi2 of L1. Okay. So this is an intersection on this side, intersection on this side. Then we can again count things. You can count solutions to this equation, which go over here and go over here, but you need to count them with some weights. And the key thing that this formula doesn't give you, or actually a corrected version of that. So we need a version of the integral u star omega, and that's not what that's well positive. So be positive is exactly what we need in order to define things over lambda naught. And what you can do basically is you can write a variant of this. What you do is something like u star omega minus integral of the ht along the line, or the hs maybe. Okay, so that's what you write down. But the issue is that this thing is not going to be positive unless minus plus maybe. This is not going to be positive so because of this term here. So positive. This requires the condition h1 less than or equal to h2. So another way to say this, and let me just say what in a different way. So you may have heard that Floer homology is Hamiltonian invariant over the Novikov field. And the reason that it's Hamiltonian invariant is precisely that you can write this equation and you can go one way and then you can go back, and those gives you two maps and you can compose them, and then you can show that those two compositions are Hamiltonian to the identity. Those two compositions are homotopic to the identity. But if h1 is less than or equal to h2, then this one will be defined over the Novikov ring, which means it will only have positive exponents. T to the lambda I, this lambda I will be greater than or equal to 0. Okay? But when you go in the other direction, then you will get negative powers. Okay? And that's fine to get. It's fine to get negative powers when you are working over the Novikov field. But if you're working over the ring, if you're working over the whole disk, then that's bad. Okay, and so this condition here is essential. Positivity is essential. So it looks like I went on some detour talking about Hamiltonians and maps relating Floer homologies to Hamiltonians, but in some sense we're now kind of done. Okay, so now comes the thing that our goal is how does the Hamiltonian enter the picture? How does the subset enter the picture? It's going to enter right now. So for each k inside of M, let's define, let's say curly h. So this is like Hamiltonians. K to be okay. So it's really some kind of category, but for now, let's say the poset of functions from M to R, which are less than or equal to 0 on K. Okay, so let's draw some pictures. What does that mean? Look at functions of less than or equal. At least. Can I do it here? Well, let's first do it just like on the real line. So that's okay. So if M, this is very symbolic. This was my M, and this is K. Okay. So the kind of function we allow is a function that does that. So this is a good function. And what is this? So this is a partially ordered set. It's partially ordered by what? It's partially ordered by, we say that H is less than or equal to, exactly like here, H1 is less than or equal to H2. If this is true pointwise, if for all x and m, this holds. Okay. So this is one function, H1. This is another function, H2. Why are we doing this? The reason we're doing this is because I said at some point, I said some words about indicator functions. So if I took if I tried to make some kind of terminal element of this, which doesn't exist, of this, partially ordered sets of Hamiltonians, that the terminal element would look like this. It would be like, oops, sorry. It would be 0 on K and plus infinity outside. And this is what I really want. What we really want is to define, so let's call it H sub K. So we want to do CF star of HK L0, L1. Okay? But that doesn't make sense because this function HK that I just is not even continuous. Well, that's the point. That's the only problem it has. It's not continuous. Oh no, it's not even well defined. Here's a value plus infinity. This doesn't make sense. But what we can do is we can approximate it from below. So what you can do is you can take the colimit over all h in this over here of the Floer groups. Well, that would be great. We take this colimit, and this is 12 modules over the Novikov ring, but this would still give the wrong answer. So the reason this would give the wrong answer is that if you took this colimit and then decided to like pass to the punctured disk, like if you did localized inverted T, that would be basically the same thing as taking the colimit before whatever. Inverting T before taking the colimit. And we know by some discussion that I kind of alluded to here, that if you invert the Novikov variable, all these maps, all the maps that you get out of the structure, the map goes, maybe it should have written it here, EF star H L1, H L0 L1 to CF star H2 L0 L1. So all these maps become equivalences. So you'd be taking a colimit over equivalences, and so it would be the same thing as the same answer as when you set h equals 0 away from the away from the origin. That's not what you want. That doesn't look good. So what is it that we want? What we want is we say, oh, this is some module over this Novikov ring. But this Novikov ring has some kind of t-adic valuation, and so we can complete it. And this completion process, the way you should think about it is that what it does is that anything that's at plus infinity, it gets rid of. So this kind of take the inverse limit. I.e. take inverse limit of f, so modulo t to the k f as k goes to plus infinity. Okay, so f is some module. So that's the definition of these groups. Okay, it's very non-straightforward definition. CF star sub k of L0. Now, in the last 5 or 10 minutes, I just want to go back to some of these properties that I said at the beginning. About why this, what comes out of this formalism. So at the beginning I said, okay, so I haven't defined the categories. I've just waved my hand at defining the morphisms in them. What I want to do next is to explain just a little bit sort of where does the restriction map come from. So so intuitively, the restriction map comes from the following picture. First, I want to do the intuitive thing, and then it turns out that actually, practically, it's even easier than that. But it took a while to get to the thing that makes the definition straightforward. I think somehow the picture is important. So, okay, here's M. Remember, there is some kind of K. I forgot where I had my K's and flip primes. I'm sorry. That K is a big thing or a small thing? Anyway, it doesn't matter. So let's say that this is the big thing. Okay, this is some kind of indicator functor for K. And let's look at the same thing for K prime. Maybe my K prime. I feel like it was the other way. Oh, sorry. Oh, anyway, this is K prime. I think it's reversed. So now I just want to point out, like, it's clear that this red function is greater than or equal to this yellow function. Okay. Red greater than or equal to yellow. So by the principle that's over here that says there's always a map from the small thing to the big thing, we should get CF star from small thing to the big thing, K CF star. So that's the picture. In practice, it's, as I said, it's somewhat even easier because what I said, I defined these things out of some completion, of some co-limit. Okay. The completion parts, well, that somehow clearly doesn't care about K or K prime. The co-limit part, comes from these categories, H sub K. But these posets, they're very simple posets. They're just posets consisting of functions satisfying some property. If I have a function which is less than or equal to 0 on K, well, then in particular, it's less than or equal to 0 on K prime. This is we're looking here. Then in particular, it's less than or equal to K prime. So we just have some inclusion from HK to HK prime. I mean, this is like literally like just inclusion of posets. And if I have 3 of them, then I ran out of colors. Then I just have triple inclusion. So if you want to go from, inclusion of posets to some map on Floer homology on these morphism spaces, what you then just need to know is, as long as you have some kind of functorial way of taking the colimit, well, that should be okay, except that hidden in the fact here is the fact that I'm trying to take some colimit of chain complexes, so probably this should have been a homotopy colimit. But let me just hit that. So functoriality of colimit gives, colim over H in here, F star H L0 L1. This maps to colim over prime, HK prime, F star H prime. Okay. And then you complete. The problems, I mean, the constructions are very complicated, and then you have to ask yourself, like, how do I compute anything? So, and this was why at the beginning, what I explained was the computation for S2. So the computations cannot be done directly. At least I cannot do them directly. But, for example, if you go back to this S2, it's actually quite interesting. Combine everything that I said. So what I said, the Fukaya category support in this little region here. Okay. The restriction map from the Fukaya category, the whole thing, to that Fukaya category is an equivalence. And so in particular, it means like if I took like this Lagrangian, some kind of equator that's tilted, and something which is even more complicated. Just some circle, L1, which is just some smooth circle. Bounding area 1/2. Then even though even though I cannot really write down for you what is this chain complex that, of the morphisms between L0 and L1, because, I would have to write down all the functions on the LS2, which are less than or equal to 0 on here. And for each of them, I would have to compute this Floer group. And then I would have to take this co-limit and obviously take this completion. That's completely crazy. That's not something I can do explicitly. But the answer over the Novikov field the Floer group, sorry, CF star. Okay, 0, 1 over the field. This is basically mu invert T is isomorphic. Is it? Yeah, not isomorphic. It's quasi-isomorphic. Has the same cohomology. Homology as what we said at the beginning. Cohomology of S1. And so this, is not quite does not quite exemplify the kind of situation where we have this locality statement that we said before, but it is the first case where you can at least see some method for computing these local groups. Now, the reason that this machinery is being developed is so that once we understand how to compute them well enough, and once we can understand how to prove locality, then, in some sense here I went backwards. I said, we want to understand the local group so that we can compute the global thing, but actually in this case, the only way that they can compute the local thing is by the global thing. And the goal is in general to go the other. Okay, thank you very much. But really,
Questions?
So one question, I think it's just a typo.
yeah.
H originally was a family of Hamiltonian.
Yes.
Isotopian.
I just admitted that. So this condition, the easiest way to, there's some more general versions, but it can just be like this. You can do it like that. You can also just, basically the theory, this specific theory doesn't require, so this word, so when the function doesn't depend on T, we call that the autonomous case. Okay, the actual definition of these groups doesn't use anything other than the autonomous case. But the statements about like displaceability that I said, those, there are subsets which cannot be displaced by autonomous things, and for which we actually need a non-trivial notion. Well, non-trivial things. That's why I introduced it. Probably it was not essential for the discussion. Done.
Yeah, so when you were talking about the Viterbo factoriality thing, you also
This is what we call Viterbo factoriality. Good, I like this. Yes, it is.
Okay, I guess the other thing that you could possibly call Viterbo
Okay.
factoriality.
Yes, that I talked about yesterday. Yes.
Yes. So there you would also need to define this for M symplectic manifold with boundary. Is that
so?
Like, for example, these four.
Okay. So again, for experts, the way that I presented it today, the only thing the only structure that exists on M is a symplectic structure. And if you had an exact symplectic structure, then you could build a variant of these categories where instead of completing using the Novikov ring, something like that, what you would do is you would use the action filtration, and you would complete with respect to the action filtration, and then but you would get something that's still just like k-linear, rather than filtered and k-linear, rather than something over the Novikov ring. So in some sense, there's two versions of this story. Like there's this story for local Fukaya categories of closed symplectic manifold. There's also some story for local Fukaya categories. Fukaya categories would support on exact symplectic manifold, where again you use the action instead of using the Novikov variable for completion purposes. Does that help?
I guess I'm like you can sometimes do Floer theory on things that are not exact and
Yes.
back them with boundary. So is that
So you want to do things? Yes. So that's we're not. So it's quite annoying to try to define this for K, which is non-compact. It's hard to set up the correct generality, but it is possible to do so. In our paper on the Hamiltonian Floer theory, on frame D2 structures, we allowed M to be, I think we allowed M to be non-compact, but we still only had compact subsets of it. It's, you know, we can do things more generally. If you do things more generally, then basically you're heading towards something that will combine what I'm saying with like Gadacha-Parton-Shende. So it's possible to combine both, but that's not what we plan to write up first.
Thank you.
How does this interact with the higher infinity composition?
Oh, I didn't say anything about it, but
It's automatic. Or?
splendidly. So the way we set it up, I mean, we you know, okay, so I said that there is some partially ordered set of Hamiltonians. But actually what you can do, so if you just basically think about it from the beginning, I'm trying to say something derogatory, but trying to figure out how to say that. Like, if you think about it from the beginning, like from some kind of totalitarian point of view, where you just say like, we should just keep track of all the data and not allow any choices. Everything should be fixed at the beginning. Then in fact, it becomes much easier. So what I mean by that is here, I already made my life much easier by saying, let's take all Hamiltonians and take the poset of all of them instead of picking a sequence. If I had this normal thing to do usually, but you know, symplectic topologists are like anarchists. We don't like order. We're like, just pick a sequence. It's just, in the end, then we'll just compute the right thing. But if I pick the sequence, then I would have to relate the sequence associated to K to the sequence associated to K prime, and there would be a mess. Okay. So similarly with the A infinity composition. So just this is a poset, it's some type of category. In fact, there is some kind of like multi-category. But each tensor, some kind of category, where the morphisms are like all possible ways of writing some kind of Floer data on some strip with some appropriate conditions. You just do that. So all the data that there is. And then, you know, this colimit turns into some kind of like con extension from this forgetful functor from this multi-category to A infinity. Okay, that's what you do. And just some huge, just absolutely, just don't, you know, just keep track of everything and just do everything formally. But if you do it like that, then yes, everything is tautological and all functors strictly respect the A infinity structure, and there is just no homotopies. Kind of insane, but that's just how it works out.
Bounding cochains do not.
Bounding cochains are more complicated story, but I remember at the beginning I said, so that's actually the one thing that's not completely satisfactory with how we're writing things. I mean, no, I'm sure there's many more things that are not satisfactory, but the one thing that is most unsatisfactory, and that is we say our objects are Lagrangians in M with bounding cochains. We fix a global bounding cochains. There will be examples where there's some Lagrangian, it has no bounding cochain as an object of the global category, but when you restrict, it should have now a bounding cochain. But that theory is, well, this theory is a lot of fun actually, but that would require kind of even more new homological algebra of curved A infinity things, which doesn't exist yet. So anyway, yeah.
Any other questions? Thank you for coming again. Right, we can show up here.
Sometimes if you'll be yeah. Fix this sequence. Also bounding maybe like it's like unfair. It works in theory, but I think that's not. So I mean, yeah, I believe it.
Sobald du zwei Krümmungen hast, weil du Krümmungen hast, die verschiedenen Formen die Chits. Egal, also für Lie Group, wenn du hast du so eine in höheren Krümmungen hast, halt so eine Art Beliebigkeit, die zu definieren. Ja. Kannst ja immer shiften.
That's like a different category because it's different. Objects are going to be Lagrangian together with choices of.
Genau, da wo die
You know, take the symplectic form, there's a one form on the Lagrangian. The Lagrangian has to have a choice of primitive for that one form that has sort of function. So that's not anything.
Connection.
So what I would say is, you don't say, in that case, you just say, I work with filtered.
Irgendwas sind ganz toll, die transformieren dann halt.
Filtration is determined.
So, also es gibt so Korrekturterme, aber im Wesentlichen, was passiert ist, dass du
What I'm trying to say here is,
Terme,
in that case,
die Wirkung
basically you don't have to take these completion.
Transformation.
You just
Normalerweise hast du so Gauge-Transformation in dem Model.
take these things.
Das sind so eine Wirkung.
That's filtered complex. And that is sufficient.
Und normalerweise, das Naive ist einfach die Inverse Acting on, was weiß ich.
What I'm trying to say is that so in the photo case, if
Diese Wirkung wirklich.
some say negative,
Was so ein Cover dazu. Ne? Die Form.
using up and down filtration.
Okay, genau.
No, but what I want to say is that, no, like, the differential, for example.
Ja, genau, was passiert ist, genau von der Information.
It's not
And-
Dann muss ja eine Form.
And these restriction knobs, they don't shift anything.
So, ja, klar, du kannst auch mit der
What
Formel.
I'm trying to say,
Keine Formel so
continuation map,
ausgerechnet.
if you, continuation map is equal to some, yeah, Tonian. So if you use the correct exact structure on the target, at all, and
Formeln, die werden schön und du kriegst dann so
using this Hamiltonian isotope,
Von den
we're to
Words.
start that structure.
eine normale Wirkung von
They clamp on L,
linear. Zusätzlich dann sogar nicht linear.
Taylor restricted
Bei Zweikontur sieht man es noch nicht so, aber bei Hyperkontur dann.
Oh,
on
I see.
time one flow. Okay. And if I use the correct one on the time one flow, then this continuation map will actually always do these actions.
See. So in that
You'll
sense,
never see any negative.
it's really important to use like actual J-homomorphic equation with moving Lagrange boundaries.
No, actually,
it's
don't
not.
write it with moving branch. We write the Hamiltonian version.
That's right. Okay.
I just thought if I did that, then I would have even more stuff to explain.
Okay.
I would have an inhomogeneous PDE on the board, and that was I thought that would be worse than having a homogeneous
Fair
PDE
enough.
was moving. I don't know which one is better, but that's the only. In the paper, we don't use. That's how. Yes.
Very quickly, do you have a reference for this derived use theorem that you got on the board?
That's hilarious.
Just try to
so-
find something like this.
So what theorem do you think I said?
So that was you wrote something about some exact Fukaya category
Uh-huh.
in some setting, and
Yes.
it's equivalent to some category of derived local
Yes.
systems.
Okay, great. Yes. So the reference for that is you have to glue together